Well, thank you. We have a few minutes for discussion. Who likes to? Yeah, Wolf.
If social systems and economical systems, financial systems are nonlinear and complex, which they most likely are, what would be your advice to the policymakers if it is clear that whatever they do will have unpredictable consequences?
Well, that's very difficult to give advice to politicians. At least one should explain this fact to them, but usually they are not familiar with this kind of questions. Very often they do believe that they can plan everything. It's just enlightenment, which is needed here too, as in other cases.
Other interventions? Yes, please, Martin. Please.
Turn this on.
Yeah.
It's always struck me as surprising that our brains, which evolved to cope with life on the African savanna, have been so successful in understanding the cosmos and the microworld. But I'd like to ask you if you think that there may be aspects of reality which our brains are simply not up to understanding at all. There's no particular reason why we should be able to understand all aspects of reality any more than a monkey can understand quantum mechanics. And so should we not regard our knowledge as being intrinsically incomplete simply because our brains are at a certain stage of evolution?
Yes, I mean, this is a kind of an ontological question, of course. Well, I would say the answer completely depends on what kind of theory you are proposing. I mean, it depends entirely on the theory about, it might be a more realistic one or more nominalistic one. All answers given to your question are answers which refer to a particular kind of theory. I can't immediately answer the question whether there is a world outside me or not. I mean, this is a funny question in a way, which can only be asked on the background of theories of that kind.
I think I would like to give a comment. This is a fascinating question, but I think obviously, since the brain has been adapted through evolutionary mechanisms to survival in this uncertain world, to make predictive models, which requires linear assumptions rather than assuming nonlinear, complex, chaotic processes, because that wouldn't help. So the brain is, as we now know, even unable, through its own intuition, to grasp its own making. It is the natural sciences that show us that our intuition is dramatically wrong when it comes to trying to describe itself. So I think by necessity of evolutionary adaptation, the ability to know is limited, and we don't know where the limits are. But it must be limited. And what is even worse, maybe even the rules for logical deduction, which we have taken from our monkey past, which are adapted to a linear world in which classical physics dominates. We have no intuition for the quantum world, for example, because it was never necessary to deal with it. That even the way we deduce logically may be idiosyncratic, and that's a problem for the philosophers, of course. So I think we should be very, very humble.
We are in the lucky situation that later this week we will have that study group on neurobiology, and I hope there will be some clarifications at that moment to that particular question also. I invite you to put just one or two other questions in the room. Yes, please.
So first, I have a comment on the first question, and then I have a real question. So my comment is about the question having to do with the advice one might give to politicians when talking about things that are fundamentally beyond prediction. In listening to that question, I'm particularly struck by the recent events here in Italy, where a number of scientists have been sentenced to prison on the basis of their failure to give what politicians believed was the correct advice regarding earthquakes, which are notoriously difficult to predict. And so my comment in that regard is not so much a comment having to do with how to answer the question, but asking whether this body might make a statement, as other academies of science have, with regard to this situation of scientists being held legally culpable for things that are beyond their capability to predict. The Royal Society of London and the National Academy of Sciences of the United States have made statements in this regard, and perhaps this is something we could discuss in our closed session. But now to the question, which has to do with strong versus weak emergence. So I'm trying to clarify what these things mean, and I've been reading about them in preparation for this meeting and becoming more and more confused as I read about them. So in listening to your description, I got the feeling that weak emergence really is not very distant from traditional reductionism. It just requires a lot of calculation. Whereas strong emergence seems to be something that is fundamentally different. Is that in that, the way you describe strong emergence is that it was non-explainable. That is, strong emergence described phenomena that were non-explainable in terms of microscopic processes, whereas weak emergence was something that, if I've understood correctly, might be difficult to explain, but nevertheless was explainable. Is that a proper description of what your distinction is between weak and strong emergence, or could you give perhaps a more complete description for me?
Thank you very much. I mean, that is a correct description. I mean, in a way you could say that weak emergence is just normal. That's a normality we are dealing with in science. Strong emergence in a way is a theoretical possibility. We can talk about what strong emergence is, or what we would call strong emergence. But for our everyday work or theory building, it's almost always weak emergence, because this is some sort of a relation between the elements and characteristics of a system.
A little bit more concrete, would you, well, I'm giving away part of my talk, but would you agree that something like ordinary superconductivity, which is now generally believed to be explained by the Bardeen-Cooper-Schrieffer theory, but that it would have been very difficult for anybody to have guessed or imagined superconductivity based on the properties of electrons in metals before the phenomenon was observed? Of course, it was observed before we understood quantum mechanics, so perhaps the question is not perhaps all that well posed, but something like that, where you could imagine, here's electrons in metals, ask somebody, what's going to happen when I cool this down? Well, I don't think that before the phenomenon of superconductivity had been observed, anybody would have guessed that if you cooled it down at some non-zero temperature, it would become superconducting. So would that fall into the category of weak emergence? Because eventually we did explain that. People did explain it. Yeah. And then what would be an example of strong emergence? The emergence of something like human consciousness, self-awareness from neurons and electrical impulses and biochemistry. What would your examples of, say, an archetypical example of a weak emergent phenomena and a strong emergent phenomenon be?
Unfortunately, I cannot give you examples of a strong emergence because there is no possibility of some kind of a prognosis. I mean, if we just invent some sort of phenomenon, we always do it on the background of a well-known theory and testing the consequences of a theory. But again, normality would just be weak emergence.
Well, I think for me the best example of a very strong emergence is the first appearance of a living organism. So, but I mean, that's kind of thing, we have no answer so far.
It almost begs the question of what does one mean by a living organism? For example, is a retrovirus the right thing, or is an actual cell, which is a lot more complex? Now I think Martin wants to say something.
Well, I'd like to question whether there is really this distinction. Let me give an example. Fluid mechanics. Fluid mechanics is a quantitative subject where the concepts you introduce are turbulence, breaking waves, and things like that. When you do fluid mechanics, you don't care about the atomic structure of the water, whatever it is. Nonetheless, in principle, we all believe that a breaking wave is a solution of Schrödinger's equation. So this is just an example where we don't believe there's anything new beyond Schrödinger's equation, but nonetheless, a useful explanation does not involve solving Schrödinger's equation. It involves concepts appropriate to the level of the subject, which are, in that context, turbulence, Reynolds numbers, and things like that. And so I'd say that's an example, and I don't see anything qualitatively different between that example, where you have a set of autonomous concepts, but nonetheless it is a consequence of Schrödinger's equation, and a more complicated system like life.
Well, there was Antonino Sikiki who wanted, but I take that occasion that's the last question, and then you can just continue with your presentation, if you agree.
I just wanted to make a telegraphic remark. The superconductivity is an example of UEEC event, namely unexpected event. Do you hear me or not? Is it working? Superconductivity is an example of unexpected event with enormous consequences. No one could have imagined that in a conductor, two electrons could be coupled and behave like a boson. This is the origin of superconductivity. As we will see in my lecture, this was totally unexpected.